All right. So now let's elaborate a little bit on crystals and crystalline materials and talk about packing. So that's going to become very important in the study of crystals. So let's simplify it first. Instead of going straight to a three-dimensional structure, let's look at two dimensions, right? And let's look at the packing of those equal size spheres, because we talk a lot about those because we kind of approximate atoms as equal size spheres. All right. So if we have something the same size, and we think about kind of rows of how we put things together, right? So the closest row we can put together is these circles touching, right? So those four in this bottom row are touching. So if we want to make a two-dimensional structure, then we have to have another row on top of it and another and another. And so where those rows are relative to the first row defines the packing, right? So in this case, we called this bottom row A because this is where, just kind of to represent where the positions are. And if we basically do the same thing, so we have another row and the circles are basically right on top of each other. So we have a circle here, another circle right on top of it, another circle on top of the second, and so forth, right? So that is the same sequence, so A. And so basically this packing is A, all the way up, right? And so, visually, you kind of look at the empty space in between these circles, right? Now, excuse me, let's compare it to doing it slightly different. So the bottom, again, those are all touching. The bottom row is A. And then instead, we shift everything half a unit over, so that the bottom of a circle is in the kind of the void space between two circles on the first row. And so we call this AB, and then we repeat the structure. So it goes A, B, A, B, A, B, right? And so we look at the empty space here. The circles are blue, so the white is the empty space. So you see the empty spaces here are much smaller, right? So just visually, you can see that this is more efficient because it's got less empty space than what we see over here, right? And so this is going to be a way of looking at how densely packed materials are, right? Because we can now kind of relate this to density in materials. This is very or relatively low density. This is a relatively high density material if we're looking at this two-dimensional structure. And so because of this alternating sequence is more efficient. It minimizes the empty space and therefore kind of lowers the energy if we think about it in this way. The other thing you can kind of note here, so there's more empty space, but also if we look at one atom right here and we look at all of the things touching it, right? So the thing's really close to it. It's got four what we'd call neighbors or nearest neighbors, right? So four spheres around it. However, if you go over here, right, and look at the same thing with the things touching it, here there's 6, right? So it's got more neighbors or nearest neighbors. And so that's another way we can kind of visualize that same thing. All right, so let's get into kind of how we define things and how we characterize these regular arrangements, so order, right? So that gets into the term crystal structure. So what is a crystal structure? So I like this definition from Structures of Materials, not our course textbook, but a different one, where it says a crystal structure is a regular arrangement of atoms or molecules. And so the idea here is it's regular. If it's regular, then we can predict the positions of atoms based on the positions of others. And we can do that, in this case, by what we call translational symmetry. So basically moving in the X, Y, or Z directions, we can predict where the next one would be, right? So because everything is very ordered, if I know the position of this first atom, then I could know that the one over here, the one up here, and the one here by some translation of X, Y, and Z. And that would allow me to determine the position of every single structure, because it should be in the position, an ordered position, right? Because this is a very ordered periodic structure. All right. So looking at these two-dimensional arrangements, regular arrangements, we can think about these by looking at what we call a repeat unit, or sometimes referred to as motif. This is something you might have learned in an art class, but that's basically the kind of lowest denominator, the thing that we can kind of repeat to make a larger pattern. So, for us, if we think forward, this might be an atom, this might be a molecule, or it might be an ion. And so basically, we put that motif onto a point structure, a point pattern. So this is known as a lattice. So this is what we'd call a point lattice. So by combining the basic repeat structure to this point lattice, if we put the motif on every point, then we get the structure here. And so this is the equivalent of our crystal structure. And so that's kind of how we're going to look at it. We're going to put together an atom or molecule, which is a motif, onto a basic lattice, which defines the kind of periodic structure, and that'll give us a crystal structure. All right, and so we've done it in 2D so far, but we're going to do the same thing for 3D. And so that's where we get crystal structures. So in this case, we take our motif or repeat unit, which we can also make kind of bigger. And in this case, we can look at a unit cell, so we can look at a specific volume. And so if we take this kind of as our motif, then we can repeat this over and over again and make the larger crystal structure. But we're doing the same thing. We start with a unit cell, or sorry, we start with a motif, which could be an atom or it could be this unit cell. And we keep repeating it on a lattice to give us a crystal structure. All right, so the first type of crystal structures we're going to talk about are going to be metallics, so those coming from metals. So you remember back to bonding, we talked about those ion cores and the sort of electron cloud. Well, the ability, the crystal structures here tend to be very densely packed, so very low on the energy curve here. Because of this type of bonding, because we have these ion cores, we can make it very dense, and they all have very similar ionic radii. There's nothing directional about it. These electrons that are floating around tend to kind of shield the ion cores, and so that's why they can get closer to each other. So these are getting closer to each other, and again, that all lowers the bond distance and minimizes the energy. So in the next section, we're going to take a look at some of the more common structures, and those tend to be, I shouldn't say common, I should say the simpler structures, and those tend to be those of metals, and they tend to be, again, very dense because of the bonding that we saw in the previous chapter.